Okay, last video of the year. Woohoo! Vertical springs and pendulums. So everything that we've learned in the last video about horizontal springs also applies to vertical springs. We just kind of changed a couple of the variables. So instead of x, we change it to y of t equals a cosine omega t. And omega is actually still square root of k over m. So that doesn't change. What does change is that when you add the mass, so if you have a spring hanging, okay, and then you add a mass, this little change here is known as delta L, because now the equilibrium has been changed. L is just a distance, whereas y would be displacement. So we can say that spring force is equal to negative k delta y. So y is negative in this case, but the force is positive, it points up. And with L not mattering for L, k delta L is equal to the force of the spring, and still points up. Okay, so that's because L is a distance, and that's this change here. And K is, Y is a displacement, and that's negative. And you go down. So if we're using Newton's second law, F net equals the sum of the forces in the y direction, and we have the spring force pointing up, force due to gravity pointing down, and this will be equal to k delta L minus mg, all equal to 0 because it's at equilibrium. This gives us L is equal to mg divided by k, telling us that the length of the stretching depends on the weight of the block and the stiffness of the spring. This makes sense. If I add a bigger weight, L will increase. If I add a weaker spring, L will increase. So for the pendulums, we can break up two forces acting on the pendulum. So if I have a pendulum here of length L, that's the length of the pendulum, and it's swung out S, because remember we're now in arc length, theta, we can say that theta is equal to S over L. And the force is acting on it, so if I do a free body diagram, I'm going to have tension and the force due to gravity. Now, for pendulums, I want to break up the two forces acting on the pendulum into radial and tangential components, because that'll get me my restoring force. We'll make it a little bit more clear. So if I do that, I have Fg radial, and I have Fg tangential. So the sum of the forces in the radial direction are equal to 0, so that's tension minus Fg radial. And the sum of the forces in the tangential direction is equal to the acceleration in the tangential direction times mass. And that is equal to the negative force due to gravity in the tangential direction. So if this is theta, right there, that's theta. Oh, that's really small, sorry. So FGT, FG, FGR, and then that's theta. This little angle here is theta. Negative FGT equals negative mg sine theta. So I can then say that these m's cancel, so I'm left over with AT equals negative g sine theta. Now, remember that the equation for acceleration is the second derivative due to position. So that leaves me with the equation for motion for a pendulum. Now, an interesting thing about sine theta, that um, any angle less than 10 degrees, it's actually better if it's less than 5, but for our work here, it'll be less than 10. Any angle less than 10, we can say that sine theta is probably equal to theta. You can check this out on your calculator, and it actually works really well, like I said, up to 5 degrees, and pretty well for less than 10. After anything greater than 10, um, it starts to get messed up really quickly. Um, so then I can say this equation then is equal to negative g theta, like I wrote up over here, theta is equal to s over L. So equals negative g over L s. Now, this is actually similar to the spring. If you look, we said d squared x over dt squared equals negative k over mx. This is s here, and we just have a different fraction, different pair of constants. So we can then conclude then, if I plug in those same equations for cosine and sine, I'm going to get omega squared, so this is the acceleration, a negative cosine omega t equal to negative g over L a cosine omega t plus b naught. This term cancels, this term cancels. So I'm left with omega equals g over L square root. So even for a pendulum, the period doesn't change, like I've said before. Now I've just proven it mathematically. The period doesn't change based on how far back you pull the pendulum. It only changes based on the length of the pendulum itself. So a pendulum of 1 meter versus 2 meters will be different, but if I pull them back at, say, 5 degrees versus 10 degrees, the speed doesn't change. Okay? So that's it for chapter 14. I will see you guys in class. Bye.